All right, great. Just. Oh. Yeah, while we turn off the light, feel free to interrupt me at any point during this talk if you have any questions, if I'm not making sense. Yeah. And before we get started, so who here does computer vision by a show of hands? Who here does robotics or? All right, I should not say too many bad things about robotics then. All right, so let's get started. So in computer vision, we torture images in all sorts of different ways. And we label every single pixel in an image, which is semantic segmentation, you can see here. We draw funny boxes around images to find all the objects. We find similarities between objects and images, and we even track key points and facial expressions through time. And the funny thing is, in the last few years, all of these tasks have become kind of one standard pipeline. We feed an image into a deep neural network, and out comes magic. And that magic can be any sort of label you want. And it actually got to a point where people outside of vision think like, oh, well, why don't you just do a deep neural network? It will solve all your vision tasks. And I had to remind them, well, first of all, they don't solve all the problems we want. And second of all, they only work well on images. And images don't really capture our real world. They don't capture what we actually want to do in vision, which is understand the world around us. None of us see the world in just images. We actually see it in a continuous stream of information. And so these images only capture a single snapshot of time, and they rarely tell the whole story. And so my advisor at Stanford and my postdoc advisors at Berkeley always told me, why don't you use videos? And as a student, I was always extremely good at making excuses. Why not use videos? And so one of these excuses was like, well, a few images are often enough to capture just all the information we want, so why would I want to use videos? Or, well, all the data sets I have are images. I really don't want to use videos. Or saying that most cameras just capture images, so that's why I have more of them. Then we always just used videos. Or videos are really large. Or collecting labels for videos is even harder than collecting labels for images. And so I've seen this list of excuses from the students I worked with as a postdoc, and I see them now from my own students. And so I prepared a few slides now to just show you that most of these excuses are bogus. And so the first one, that a few images actually capture enough information. Let's look at this video here, or a few snapshots of this video here. And all you can see here, there's a guy interacting with a monkey, and you don't really know what's going on. And so this is the actual video here. You can see there's a lot more going on than a few images show you here. All right? So you're clearly missing out on certain on a large chunk of the information if you just look at a few images. Now the other excuse that all our data sets are just image-based, that's also not true. If you look at the Cityscapes data set, which is one of the largest semantic segmentation data sets we have right now, this is all videos. It's just that a few images are labeled and the rest of the video is not labeled. Now the other excuse that most cameras just capture images, I was really surprised. So I was in Taiwan over Christmas, and I could borrow one of those fancy new iPhone 8s. And so I went to the zoo with my daughter and started capturing pictures. When I came home at the end of the day, I realized that none of these were actually pictures. They were all like 1 or 1.5 second snapshots. And that's the default mode in the iPhone 8 now. And then I was a bit curious, and I was like, well, this must take a lot of space on my phone. And so I looked at how much the JPEG compression of a single snapshot of this video would take up, and how much the compressed video actually takes. And the compressed video only takes about a factor of 3 more space. So this is something that's completely feasible, and it will probably happen in a few years, that all our phones are just going to capture small videos. Now the other one, so I was fortunate enough to talk to Gary Sussman at MIT a while back, and he actually explained to me in their very first computer vision project, the MIT summer project, they they did not use an image, they actually used a video camera to capture the scene. And the reason why they used this video camera is because they couldn't load the entire image into memory. So they had to use the video camera and read out part of the image at a time and then process that. All right? So this big list of excuses why not to use videos, the first four just, they're not really true. Now, the one I buy is that videos are just really large. And if you look at the little video of the giraffe I showed you, this is about 500 megs if you would just look at the raw pixels. Now, if you feed those into a convnet, you probably make it a floating point number, so it's 2 gigs in size. And that just means you're going to do a lot more computation all of a sudden. But what I'm going to argue here is that this is not a fundamental problem of videos. This is actually just a problem on how we use videos. And if you look at how we use videos in deep learning right now is we have a video that's somehow somewhere compressed on our hard drive. Then we decompress it using a video codec and feed it into our deep neural network. And we start out with a very small and compact representation of that video, which is about 2 megs in size. We blow it up to 500 megs. And then we feed this monstrosity into our deep networks. And now, there's about 2 ways I can think of, 2 easy ways I can think of to blow up a video. One is you add a lot of random noise to it, which is obviously not what's happening here. Or you just replicate the data over and over and over again, and that's what's happening. And so then you hope that in this highly redundant data, the deep net will somehow figure out some nice patterns and structures. And it oftentimes doesn't. And so what we did in a project that's going to appear at CVPR this summer is we looked at can we actually feed the compressed video directly into the deep neural network. And I'll give you the shortest tutorial on video compression you already see. So on a very, very high level, the way video compression works is that you represent certain frames as just images, and these are called iframes. And then you have other frames that just reference the information in these iframes, and then you say that, a certain part of this picture here looks very similar to what I had over here. So I'm going to steal the pixels from this location in the iframe, and then I'm going to slightly modify them because they're not exactly the same. And so you're going to get a motion vector. This is where you steal the pixels from, and you're going to get a residual image or a difference image, which just says how much did the pixels change as they went from one frame to the next. All right? And so the simple thing we could do is we could just go and say, all right, let's just feed all of this into a deep neural network. And the simplest architecture is we just have a network that takes iframes and produces a prediction. And then we have different separate networks that take these motion vectors and residuals and also just produce a prediction. Now, this is super easy to train. It's just end-to-end training. You feed it into, you pick your favorite architecture, run it on your favorite like TensorFlow or PyTorch or whatever you want, hit the training button, and out comes something that doesn't work quite well. And the reason for this is that there's actually a lot of dependencies between the motion vectors, the residuals, and the frame that came before it. And if you look at these dependencies, in order to decode a certain frame, you need to look both at the previous frame you decoded and at the motion vectors and the residuals. And these together actually form the image. And just one of the two doesn't. And so this dependency kind of screams for an alternative approach, which could be a recurrent network, where you just where you feed in the image first, and then you feed in the difference image and the residuals, and hope that the RNN will somehow be able to capture these dependencies. Now, the RNN maintains these dependencies, but it's extremely hard to train, and it was a big source of frustration for my student to try to train this. So, first of all, gradients in this RNN are highly correlated because you're feeding in consecutive images or consecutive frames of a video. And it also turns out that the RNN actually trains at different speeds at different stages. So the image part of the RNN will train extremely quickly. It'll give you a good result after a few thousand iterations, but then the motion ones will not, and then at a certain point the first motion RNN will start to train, but then by that time the image RNN, the image part of the RNN already completely overfit to the data. And you'll never end up with a single RNN that trains very, very well. And so what we did for CVPR is we just looked at, well, can we just not do an RNN? Can we just do something simpler? And the main reason why we had to use this RNN structure is because there is this dependency in the video that just goes from the iframe to the decoded frames all the way one step at a time. So what we did is we just broke this dependency. So instead of having a dependency graph that is one frame after the other, we now trace all the motion vectors and difference images back to the closest iframe. And now all we need to decode a specific image is the iframe and these traced, back-traced motion vectors and difference images. And tracing this information back in time, you can do this in linear time, essentially just walk back one step at a time, you sum up the differences in color values, and you add the motion vectors together. And this allows you to train a deep neural network in the same way we trained the very first version, independently for every single frame of the video, except for that you have the iframe as an input to all the other p frames that follow it in the video. All right. It also has another big advantage here is we can share the features on the iframe for many, many other video frames, and the networks that we use for the motion vectors and for the residuals can be a lot smaller because they capture less information. Yes?
So for the motion vector, you also have to trace back to the residual also, or?
So yeah, I'll explain this a bit more carefully. Okay, so the only thing you actually have to trace back is the motion vector. So you jump here, this will tell you, for this pixel, I stole it from this image here, and then this one was stolen from here, this one was stolen from here, right? And so you just trace back one at a time. And as you trace back, you also always modify the pixels, the color values of the pixels with the differences. So you don't use the color values to figure out what location to get them from, but you just sum them up along that trace, and they will give you a difference to the previous iframe.
How do you obtain these motion images and also these residual?
Yeah, FFmpeg can give you this. So any video codec actually stores those internally. They're highly compressed, and so FFmpeg. If you force a student to hack FFmpeg, they will come out.
So aren't you, sorry.
Yeah, go on.
Aren't you kind of like constraining, I don't know, like, I guess like there's like a trade-off, like now you're constraining your model to work well, like you're assuming that this is a good representation in a sense, but this whereas like these other large models, they're kind of, well, you know, just let the network learn good feature representation. So it's kind of, it seems like, like they're like, yeah, complementary problems in a sense, but I guess like how much the accuracy would improve, you know, if you like had some, I don't know, better like motion.
Yeah, yeah. I mean, so certainly I'll split the question into two parts. One is, are you constraining the model by feeding it these inputs instead of the original images? And I don't think you are, because the two are equivalent. So a clever network could figure out, could get the images from these backtraced motion vectors and the original image. So a clever network could reconstruct the original image and then do whatever the image network would do.
Well,
and at the same time, yes?
So maybe the clever network could do much better than this.
Could do much better than...
I don't know, like than this representation that you're using.
No, but what I'm saying is that the amount of information we give it is the same as the original images. It's just in a slightly different form.
Okay.
And so if you would set up your network let's say if you would allow your network to have a module in there that could do linear interpolation at an arbitrary pixel locations, then you could just reconstruct the image if you would want to. So usually we don't allow this to happen, but the information is there for the network to learn this. Yeah. Did that answer the first part? And so you also had a second part of the question, which I unfortunately forgot now.
I mean, it's fine. Maybe like once we get to the results.
All right. Yes, we'll get to the results in a minute.
I mean, this is beautifully explained. It's the same number of bits.
Uh-huh.
When you start.
Yeah.
I had tried actually about 15 years ago when it came out to get the motion vectors and compute like the focus of expansion.
Uh-huh.
And the quantization really didn't allow. I mean, errors like in 3D motion were really beyond any.
Yeah. Yeah.
So you get them like ready as they are, quantized?
Yeah. So they are usually the motion estimates from frame to frame are at like blocks of 8 by 8 or 16 by 16. And yeah, to do anything if you just go one frame back, they're not going to give you a lot of information just because the quantization kills you. The funny thing is if you actually trace them back over multiple frames, first of all, the quantization artifacts kind of go away because you're not going to hit another block here, you're going to hit something in between two blocks. And so if you chain them together, you actually get a lot smoother output, as you can see here. I mean, it's not the smoothest one you would ever see, but it's a lot smoother. And so tracing it back over several steps was actually crucial to making this entire thing work.
Also the vector
And
it's fixed point, not only the...
yes. So the vector itself points to an integer location in the previous frame. Yeah, and so I'm sure you can get a lot more out of it if you would allow it to be floating point. And we can see that this is going to be very similar to optical flow. It works better if you combine it with optical flow, but not by an extremely large margin. All right, so after alluding to the results for a while, I'll just show you them. So what we did is we first just compared, so we evaluated all of this on action recognition, the UCF-101 dataset and the HMDB dataset. And here we just compare performance on...
Philipp, maybe explain the data set for some people.
Yeah, so the two data sets are just action recognition. So you get a short video clip and you need to say what the person is doing. The person can be, I guess, running, jumping around, and I'll have some more examples of these data sets actually in the second part of the talk. Yeah, so, and the goal is just from a single video clip to just predict what the action is in that video. And what we compared to here is two image-based baselines, which are just ResNets, ResNet 50 and ResNet 152. And we measure both how much computation these networks spend if you run them on the video, and their accuracy. And then we compare to two 3D CNNs, and you can see that these 3D CNNs, they take up a lot more computation because now all of a sudden you have to do convolutions in 3 dimensions. You have a lot more parameters and a lot more computation. And they don't actually buy you that much. Now, if you run our architecture, which is similar to just an image model here, and you just run it on the video, first of all, it's as fast as the fastest image model, and it's a lot more accurate. Okay? And so that hopefully answers the second part of your question, and it shows that this representation is actually can be quite a bit better than just a raw image representation.
Do you think that you have similar patterns if you change from a neural network machine to some other neural machine, or
That's
very special practice?
No, I think if you would find an equally powerful classifier that's not a deep network, I think you would see similar results. I don't think there's anything special except for that neural networks are extremely expressive. Yeah. But I don't think there's anything fundamentally tied to deep networks in here.
Could I just push that?
Yes.
The other question. It's true that under changes of coordinates you don't lose information, but the computational implications of one coordinate system or another coordinate system are immense.
Yeah.
depending upon the structure of your process. And I'm wondering what insight this gives you into the relationship between that kind of change of coordinates that you discussed in the previous question and this particular architecture. No? Are you learning anything here, or are we just?
I see. So what is the high level message here? Yeah, I think the high level message is that pixels are not as good a representation of videos as something like motion and difference in color values. That I think that actually capturing what changes in a video is probably a lot more informative than just showing you the image over and over and over again. So if you want me to give you the high level message, that will probably be it.
So you've discovered using your intuition the right change of coordinates for the states.
Yeah. So I mean, first of all, we didn't come up with this change of coordinates. This is what the video compression people came up with. What we just showed is that you can actually do a lot better if you want to do action recognition if you work on that compressed format. And I'm not saying that this is the best format. There's probably better ones. On the top of my head, I don't know what else I would want to try.
Sorry, I have
Yes.
another question. So I don't know about the details about UCS dataset, but the HMDB dataset is pretty small. So I guess I was wondering, do you think whether like these sort of trends would generalize if you take really much larger scale datasets? Because you could argue that now, well, okay, we have, I think in HMDB we have about 7K training clips, and then therefore learning this from raw pixels for these other baselines, this is difficult because there's not enough data, and therefore that's, you know, where your method is really useful. And then if we move to the datasets where we have, I don't know, like 300K video clips for training, whether you would still kind of like see the same trends here.
Yeah. So so we haven't trained it on 300K. You're referring to kinetics. We haven't trained on kinetics. We have trained on charades, which is a little bit larger than these two, but not as large as kinetics. And I'll show you the charades results in a moment. Yeah. Yeah. So we also compare favorably to kind of the published literature. If you don't use optical flow, if you just use the raw pixels, you can see a fairly large gap between us and the prior work. If you then add in optical flow to both our method and the prior work, the gap kind of shrinks a little bit. And part of it is because our motion vectors are very similar to optical flow. And the other part is just that these methods are actually highly tuned for the combination of RGB and optical flow, and they were not as highly tuned for the just RGB results. And as promised, I also have some results on charades, and it holds up well to the published literature, but it's not state of the art anymore. So there's some archive papers out there, and there's probably some of them are going to be at CVPR this summer that beat us again on charades. But what I think is really exciting about all of this is that we can do inference much faster as state-of-the-art networks by using compressed videos and by being able to use smaller networks than these compressed videos. We are quite a bit more accurate than the 3D CNNs, at least on the tasks we tried. And the input to our network is actually quite small, so you don't need to decompress an extremely large stream of images and fill up all your disk and feed that disk to your GPU. You can actually just feed in a small compressed video. All right. So to summarize up the first part, so CoVR, our method, it maintains the dependencies in a video. It's easy to train as we have independent networks and independent gradients for all frames. It's quite a bit faster because you can use smaller networks. And one thing that I haven't talked about is that the information we feed into the network is actually a lot less redundant than just raw images. And I'd like to mention that all the painful work here was done by my student Xiaoyan. I didn't have to touch the code a single time, luckily. And it will hopefully be online soon. All right, now going back to our list of excuses, we can cross off videos are just too large because you can now just feed them in compressed, and it's actually something that is manageable. Now, in the next part of the talk, I'll talk a little bit about the fact that it's hard to collect labels from videos or for videos. And the first thing I would like to look at is just how long it takes to label an image. And so it takes about an hour to label an image in cityscapes, and you get a labeling that's almost pixel perfect for the street scene here. Now, if you want to do the same thing for a 2 to 3 second video clip, which is fairly short in terms of videos, it takes a professional rotoscopist artist, which you can see the results here, about an hour per object, and if you would want to put it on Turk, it will probably take more than 10 hours. And so that's why the largest data set of pixel perfectly segmented videos is only about 50 videos and less than 4,000 frames long. And so what most people focus on is action recognition. And so in action recognition, you're just going to try to predict one global label. What is the most dominant action you're going to see in this video? And so there's large data sets for this. There's Kinetics, which has 300,000 clips, one global label, and the label is actually not even that precise. And so what I did here is I took the top result for biking through snow, and this is what biking through snow looks like. I guess the guy who is capturing the video is riding a bike, but the rest doesn't really look like biking through snow. And the bottom here is scrambling an egg, and I didn't bring the sound for this video, but you can hear the guy talk about how he's going to scramble the egg for like a minute, but he never actually scrambles it. And so these are the top videos. It's not like I had to go dig into the data set to find these. These are like the top videos in the data set. And so that just kind of shows you where we are with data sets for video tasks. And so in another project for CVPR, what I did is I hacked video games to just give us an almost infinite stream of dense labels. And these labels are instance segmentation, they're a depth estimate, optical flow between 2 consecutive frames, albedo, and some semantics for some of the instances. And I did this for The Witcher, for GTA, and for Far Cry. And you can get these labels in real time while you play the video game. And so, first of all, I started this project thinking that, yes, I get to justify to my wife why I want to play video games all day long. Turns out this is not a good idea, because if you're like 2 weeks before the deadline and you need to collect your data, it's extremely stressful to play video games while you still need to write a paper. So, yeah, I cannot recommend this. Yeah, but I'll go a little bit into detail on how we actually get these labels out now. And so on a very, very high level, the way a video game produces the stunning visuals you see is you have the video game code. It interfaces with DirectX or OpenGL, which is a graphics API. And that graphics API then interfaces with the GPU driver, and all the computation for your video game is done on the GPU itself. And then the GPU produces this pretty picture here. And so what we do in this project is we're just going to also have the GPU output all the labels we want. And the way we're going to do this is by just injecting some code in between the game and DirectX. And I didn't know this before I started this project, but Windows is extremely great for this. So you can just put in a DLL called the same name as the system DLL, and Windows will just load it into the main memory. It will just give you access to the video game. And so what you can do then is you can go mess with the memory and look at the memory of the video game, and you can also just mess with DirectX. And so to the game, you should say, hey, I'm DirectX, talk to me. And then to DirectX, it's like, hey, I'm the game, I'm going to tell you what to do. All right, and so you can just go in between, and you can just completely mess up the game if you would want to. All right, and this is great. So we're gonna use this to our advantage. And what we're gonna do is we're gonna track objects in the GPU memory of the game, and then we're gonna inject random, we're gonna inject custom rendering code into the game's GPU to render out all the label maps we want. And we're going to do this all in real time with an overhead in less than 10 milliseconds per frame. And before I'm going to go all technically deep here, there's a few things you can actually get for free by just injecting a DLL in between the game and DirectX. And so you can just get this by just looking at the right memory location on the GPU. And so obviously you can get the image the game renders from the GPU somewhere. You get albedo, which is the surface color of every single pixel the game used to render. And the reason why you get albedo is because all the games internally actually try to mimic light transport or try to approximate light transport in some way. And they all do it by factorizing the surface color and the shading of that surface in two different channels. And so if you can just go into the right location in the game's GPU memory, and you can just read out the surface color of every single pixel. And you also get the depth. So the game maintains a depth buffer to figure out what object is in front of what other object. And so you can also just read that out. And so that's already like half the stuff we just get for free. Now, if we're going to go a bit deeper, we need to understand a little bit more about the game's rendering pipeline or DirectX rendering pipeline. And so on a very high level, the way a game displays the graphics to you is you have meshes, which are just geometric descriptions of objects in the game. Then you have textures, and you can think of this textures just like wallpaper. Wallpaper that you put on top of this 3D geometry to just create a colored object. And then in the very end, you also have rendering parameters. And these rendering parameters capture things like where is the camera, where are the lights, how is the object deforming if it's deforming. And so it captures all sorts of things that should change as you render the graphics of the game. And then it goes through the first stage of processing. And that's just vertex processing. And in that stage, you're just going to transform the geometry, the meshes, and put them into the reference frame of your camera. So you just think of, you take all the objects and place them into the view of your camera. And then the second part is rasterization, where you create an image out of the 3D geometry. And then the last part is pixel processing, where you do all the fancy pixel-wise computations, such as lighting, texturing, like assigning a pixel a color, and so on. And so in this pipeline, the first part is programmable through a vertex shader, which is a lot like a little CUDA program for those of you who use GPUs every day. And then the third part is also programmable. It's a pixel shader. It's, again, just a small program that looks a lot like a CUDA program. And so what we're going to do here is we're just going to mess with these two programs here. So we're going to just inject arbitrary code into the rendering code of the game to just produce segmentation and optical flow. And the way we're going to do this is for segmentation, the key insight is that every single mesh or every single object is rendered in different parts. So for example, the wheels of the car here undergo a different transformation than the body of the car. They undergo a different transformation than maybe the seats of the car, and so on. But all of these kind of form kind of parts of objects, and they're rendered together. And now we can group these parts together by just looking at the reference frame of the object. So the way artists create these assets in video games is they create them in one tool, and they want to make sure that they're all in the same reference frame, in the same coordinate frame, so that they don't appear in completely different locations in the game. And so you can read out that coordinate frame from the GPU memory, and that will give you a way to segment or group objects together. And then you can also use the same information to track them over time. And so here's a little example of a guy running at me, trying to club me. And so you can see all of these colored parts here are different parts of objects that are rendered. And if we group them together by the reference frame, we get the instance segmentation for free. We also get the tracking just by following these instance segmentations through time. All right, so that's segmentation and tracking. And sorry, this was on a very high level. There's lots of code that does this. It's a bit more involved than I explained, but I don't really want to go into the details. Now, the final thing we're going to do is we're going to get optical flow out of this. And so what optical flow measures is it measures where did the pixel in frame A move in frame B. And so what we're going to measure here is if you're going to have a frame at time t, where did the pixel come from in the previous frame? And it's very similar to the block motion estimates we saw. It's just pixel perfect and at a very, very high resolution. Now, if all you were to render is completely static and doesn't change, what you can do is you can just take your camera projection, invert it, and then add the previous camera projection, and that will essentially project any point here into the reference frame of the previous image you rendered. You take the difference between the two, and that will give you optical flow for free. Now, this only works for static objects. It doesn't work for anything that moves around in the scene. And so for moving objects, we need to take a slightly different approach. What we're going to do here is we're going to just duplicate the rendering code for the vertex shader and just have kind of two programs that execute right after the other. For one, we give it the parameters of the current frame. For the other one, we give it the parameters of the previous frame. And now if we run this, we get the location. For one, we get the location in the current frame. For the other one, we get the location in the other frame. And that gives us optical flow. And this works for any sort of animated objects. It works for like mesh, for skeleton animations, for anything you would want. It's also extremely fast because vertex computation actually takes up less than 1% of the game, and most of the time is actually spent coloring these vertices. And so here's an example of this. So this is frame number 1, this is frame number 2, and this is the optical flow you get. And you get this all for free while you play the video game. You can also get an occlusion map out of it. That's a little bit more involved, and I can tell you more about this offline. Yes? So to a certain extent, you could. We haven't explored this much, but that's actually an extremely good point. So yeah, yes, yeah. So you could potentially see behind the object. Probably more so in albedo and not in the final rendered image, just because there's lots of optimization that doesn't try to render a single pixel that is occluded, but you could see behind objects too to a certain extent, yes. Yeah, great. And so we collected a data set of 220K training frames from 3 video games and 60K testing frames. And it's all paired ground truth, 6 FPS, and so for a part of it, for GTA, I could use the autopilot. For the other 2 games, I had to play it myself. And I'll also have to code for this online at some point, hopefully before CVPR. And so you can collect an almost infinite stream of data this way. You can record up to 15 FPS, and if you don't want to store it to disk, you can probably get about 30 FPS out of this. And it's quite general. It works on quite a lot of games. So this, like 2 hours before the deadline, I had the great idea. Well, why don't I try another game to get one more segmentation out? And so it took me about half an hour to get this segmentation by just hacking in a completely new game. So once you got a feel for it, it's actually quite efficient to just go and apply this to more and more games. All right, and so. Yeah,
so you can potentially do super resolution also, right? Because you have a boundary.
So, all right. So, can you say that?
Mm-hmm. Objects, right?
Yes.
So
yes.
Limited the resolution that you're rendering.
Mm-hmm, mm-hmm. Yeah. So if you, it's a bit hard to extract the geometry in real time. But if you were to extract the geometry in real time, or somehow save it, like you can save the geometry, it just takes about half a second to save it, and then you can get probably an arbitrary resolution if you'd want to, yes.
This isn't research related, but I imagine you had maybe some licensing issues if like people complained that you
Yeah. So that is a good question. Yes. So first of all, I'm not the first one to do this, and people just do it and hope they will not get sued. Now, the thing is, you're not allowed to publish the code for the specific video game you do because that contains some reverse engineered information. Now, like DirectX is already to a large extent reverse engineered, and so that part of the code that can easily be distributed. And then there's just a small part that depends on the specific video game that will probably not be able to be put online. There's also a very big gray area about what parts of the game can you publish. You can show screenshots, but can you show albedo? Can you show flow? It's a gray area that people are currently figuring out. Yeah.
So have you tried, I don't know, like building models like on the synthetic data and then trying to use it for something on the real data? And so for example, I assume for GTA, I mean, like that's very useful for like autonomous driving and for games that like Far Cry or Witcher. I'm just wondering like where you could actually use this. Like,
So for robotics, I know there's some exciting research at Intel Labs that showed that you can transfer from a simulator that's not GTA, but it's CARLA, which is a similar simulator, to real-world little toy robots, and that would work. We did for GTA. We have one project in submission right now where we just show that you can do the task, you can learn semantic segmentation in GTA, and it transfers to a certain extent to cityscapes, which is the real-world equivalent to it. And so that just becomes an entire business of its own, like trying to transfer these representations. And I can talk more after to talk about this. So in the last part of the talk, if I still have some time, I'll talk a little bit about one very recent project, which is kind of I'm really interested in acting in these video games because I'm old enough that I don't need to play them anymore, so I just want my computers to play them. And so as a computer vision person that's completely ignorant of robotics, the first thing that came into my mind is like, well, why don't I just play the game a little bit and just imitate whatever I did and kind of and just do imitation learning. And it turns out like for some games it works quite well. For GTA, I couldn't quite get it to work. And then I got kind of sucked into reinforcement learning. And reinforcement learning, for those of you who don't know, it's all about optimizing this thing here. Not all about, but it's optimizing. It's all about optimizing the expected return of a policy in a certain environment. And what I'm showing you here is you're going to have a certain policy, which is just, say, an agent that plays the video game. It plays the video game, and as you play, you collect trajectories, which can be series of frames. It can be states inside the game. And then you're just going to measure how well you did. And this is my ignorant part of the presentation. If you did well, if you stayed in lane, it says you did good, you get a higher reward. If you crash, you don't get a very high reward. And this also doesn't really help, okay? And so all that reinforcement learning does is it just says, well, I want to do more of the good thing, driving well, and I want to do less of the crashing. And the amazing thing about this, which still is miraculous to me, is that this is actually an objective that you can optimize using gradient descent. You can just backpropagate through this entire thing using reinforce, and you can learn something. Now it's not very sample efficient, and then so just vanilla reinforce wouldn't work on a game like GTA or in a simulator like CARLA. And so instead, people came up with these efficient lower bounds for the reinforcement learning objective. And examples of this are trust region policy optimization or proximal policy optimization. And so what we did for ICML is we looked at these, and we actually came up with a slightly tighter lower bound than TRPO and PPO, and it's also mathematically correct. Not implying.
What is the state here?
Yeah.
For your case, what is the
In my case, so I did both CARLA, where the state is just images of the car that come in. Then also the continuous control. That worked a lot better, and there the state is just so you're trying to animate a character, and the state is just the joint angles. Yes. All right. And so it actually turned out that getting a tighter lower bound than TRPO and PPO is actually surprisingly simple. And so all we needed to do is we needed to kind of find a hammer, which is if you look at the expectation of a certain function over two distributions, P and Q, then the difference in these two expectations is just bound by the maximal function value of the function you're looking at, times the square root of the KL divergence between the two. And so I asked one of the theory guys at UT, is there a reference I should cite for this? And it's like, Philipp, this is trivial. You don't need to cite things. You don't need to cite papers for trivial things. And indeed, like the proof is like 3 lines long, and then you add Pinsker inequality, and you'll get this nice little hammer. And so what you can do is you can just apply this hammer to just vanilla the reinforcement learning objective. And if you apply it to the difference in expectation under one policy that's an oracle and another policy that you're currently optimizing, you actually get a very nice result that shows that imitation learning, just imitating another policy, optimizes a lower bound to the expected return in reinforcement learning. And so the obvious thing here is if the KL divergence, if the two policies are the same, obviously you'll get the same return between the two, but it also falls off in a fairly predictable and nice way. But this objective by itself doesn't really give you a way to improve upon your current policy. And so if you make this lower bound slightly more complicated by introducing an advantage function, you can get a lower bound that actually gives you a clear way of improving upon your previous policy. So now you can actually do better than the policy you're trying to imitate, or you can do better than a policy that you're currently trying to optimize. And so this gives you a way to continuously increase or the performance of your policy. And so that's what we do in reflective policy optimization. We just optimize this lower bound. I can show that this lower bound is tighter than the lower bound that's used that's at least mathematically used in TRPO, not tighter than the one that's used in practice. It's guaranteed to improve it's guaranteed to improve as long as one of these advantage values, which kind of shows how much better you could do if you take action B over action A, as long as one of them is positive anywhere along any of your samples you collected, you can improve the policy. And again, it's mathematically correct without any approximations. And it's also quite flexible. You can actually play around with it. And you can show that you can have both a batch version of this, or you can have replay memory in it, and it still mathematically works out. And you can even have a hybrid approach between imitation learning and reinforcement learning, where you sometimes just look at the trajectories you get from some oracle, and other times you just look at your current policy, and you're still guaranteed to improve the performance of the policy you're optimizing. And so we compared this to TRPO and PPO on some continuous control tasks. And I mean, on these, all the algorithms actually work almost the same. This is the Acrobat, this is the mountain car. Now, what I would like to point out here, though, is that I did this over 16 runs on our cluster. And what I'm showing you here in the kind of the error bars here is what the variance was between these 16 runs. And you can see that green is our approach, RPO, that the variance is actually a lot smaller. So we get a more consistent result across different experiments. And it also works quite well on the RoboSchool continuous control task, where you again compare to TRPO and PPO. And here, 1 just means it's the best method. 0 would mean it's no better than just a random initialization. And anything in between is linearly scaled. And so you can see overall tasks in the RoboSchool, the reflective policy optimization does best. And then finally, we also tried it on a driving simulator, which is CARLA, which is developed by some guys in Barcelona and Intel. And in CARLA, you essentially get to see a picture in the reference frame of the car, and your goal is to produce acceleration, braking, and steering patterns. And in that one, we compared to A3C, and we do a lot better in the training environment, but just like A3C, we don't really generalize well to the testing environment yet. And I would certainly not drive with this. Yeah, so this means that only in about 12 or 13% of the cases we managed to get it to take a turn. And in the other cases, we just ran into something. So it shows that there's some more to be done. And I think part of the thing that needs to be done in the future, and I hope somebody will do, is that I feel like we need to move a little bit away from model-free RL. And here's a little example. This is not me driving. This is a person driving. But you can see this is a long sequence of actions, and eventually it results in a crash. And now, what do you think? If you think of reinforcement learning, what reinforcement learning does, it says, "Oh, that was not good. You crashed." Okay. And now you're just going to say, "So, now figure out what you did wrong." And then you just repeat this often enough in the hopes that somehow eventually the algorithm will learn what's right and what's wrong. But I feel like going forward, we need to kind of give it a lot more explicit supervision, and maybe even give it a model of the world to reason on, to be able to quickly assign blame to wrong actions if you want to do reinforcement learning, or just try to go forward in a direction that's maybe a little bit away from RL. And I'm happy to talk about this more offline. And if there's any more questions, I'm happy to take them now.
We have time for questions. So we started the work actually asking about representation of images and videos.
Mm-hmm. Yes.
And,
yes. Sorry. It was a long trip. Yes.
Yeah, so coming back to that representation issue, what do you think that really the video can give you in terms of representation that's not getting out of the single picture?
Mm-hmm.
So I think the first part you talk about flow, then
Yeah.
the last part really talk about actions.
Mm-hmm. Yes. So going forward for actions, I think what videos can really give you that images don't is anticipation. Like you can anticipate things. I think you can anticipate things a lot better in a video than you can from a single frame. Like it can ambiguate. Like if I throw this into the air, you don't know if it's going up or down. In a video, you know instantaneously. So these sort of, like, it certainly gives you motion. It gives you what's going to happen in the future. That's something that probably you gain the most from in videos. But also just for understanding, I think like if you want to build a persistent model of the world, if you want to know what's behind the screen here, a video can give you this. If you go look behind it, an image cannot.
People are still thinking about video games.
That's a wonderful talk. I wonder if you could comment a little bit on what you think challenges are in accomplishing this dream sort of transfer from sort of synthetic environments to real environments.
Yeah. So I currently think there's two ways. There's probably two avenues I would like to explore here. One is maybe synthetic environments could just help you figure out how to solve the task, and then you just collect the right amount of labels in the real world, and then just solve it using a supervised learning problem. So the synthetic environment might just be able to give you an idea on what the right approach is and how you can get it done. Now, that's I hope that's the minimum it can give you. I hope it can actually give you a little bit more, and I think what you actually need to do well here is you need some, first of all, you need some common task or some common grounding, and that can either be by finding correspondences between the real world and video games, and we have seen great progress in image-to-image translation between the two. It could also be on a more semantic level, where you just say that you kind of want to associate the same objects with one another, or yeah. I think that's in the first stage, and obviously the real world is much more free and interesting than the video game is, and that's the second part, and I have no idea how to do this. Yeah.
So, the image capture
Yeah.
came about because many years ago, object recognition is hard,
Yeah.
data recognition is hard.
Yeah.
So people started by using this capture to both train a machine and also check whether you're human or not.
Yeah.
Can you think of ways, advancing, obviously capture can be solved as neural network now, but do you think by playing a video game, we can replace the capture kind of thing?
Yeah, I mean,
Just log in and
yeah,
play the game first.
yeah, but it only depends. It depends on how much faith you have in RL and this entire community, right? I have a lot of faith.